First of all, good morning and good afternoon for all the participants in this session. As you know, this session is about battery storage technologies and their potential applications in the power systems. To make a quick introduction, as you know, electrical power infrastructures are changing dramatically around the globe due to smart grid initiatives, the establishment of renewables and the resulting distributed nature of creating electricity, the need for independent microgrids to ensure grid reliability, new demands from end users, the need to reduce greenhouse gas emissions, as well as the capability to accommodate mixed energy resources. As a result, the power network faces great challenges in generation, transmission, and distribution to meet new and many times unpredictable demands of providing current electricity supply. And battery energy storage, what we call BES, has been considered a game changer with a number of technologies that have great potential in meeting these challenges. However, the wide variety of options and complex performance matrices can make it difficult to apply specific BES technology for particular applications. This presentation intends to contribute information that will give a smart grid user a clearer picture of the state-of-the-art electrochemical technologies available and where they would be suited for integration into a power generation and distribution system. So thank you very much, Professor Lee. Our presenter, I will tell you a short biography of our presenter, Professor Lee. He has received the BS and Master Science degrees from National Taiwan University, Taipei, Taiwan, and the PhD degree from the University of Texas, Arlington, all in electrical engineering. He is currently a professor of the Electrical Engineering Department and director of the Energy System Research Center at the University of Texas at Arlington. He has been involved in the revision of several IEEE standards. He is the president of the IEEE Industry Applications Society and editor of IEEE Transactions on Industry Applications. He's the project manager of IEEE NFPA Collaboration on Arc Flash Phenomenal Research Project. Professor Lee has also been involved in many research areas of power systems, in particular utility deregulation, renewable energy, arc flash hazards, and electrical safety, smart grid, microgrid, many topics, and of course in energy storage systems and electrical vehicle charging infrastructure design, big data, etc. He has served as primary investigator or co-primary investigator of over 100 funded research projects. He has published more than 190 journal papers and 290 conference proceedings. He has provided on-site training courses for power engineers in Panama, China, Taiwan, Korea, Saudi Arabia, Thailand, and Singapore. He has refereed numerous technical papers for IEEE, EAT, and other professional organizations. Professor Lee is a fellow of IEEE and registered professional engineer in the state of Texas. So again, thank you very much, Professor Lee, and you can start your presentation whenever you want. Just one comment at the end of the presentation for the participants. Professor Lee can answer some questions, so please write down them on your chat window, and we will go to that question at the end of the presentation. So please, Professor Lee, go ahead.
Okay, good day, everybody. And then, yeah, it's nice. I haven't never been to Uruguay, but well, that is use this virtual platform. Then I have a virtual visit on the country. And yeah, today I would like to share with you or discuss with you on the battery storage technologies and their potential applications in the power systems. And well, first, thank you, Mr. Chairman, and then for basically a good introduction. And then, as we know, the electrical power system infrastructure are changing dramatically, okay, since 1990s. And then they start the deregulation, and then also the move to adopt the renewable energy. So as a result, the power network face great challenge in generation, transmission, and distribution to meet the new and the many times unpredictable demand of providing coherent electric supply. And I believe everybody watched the news on the COP26, and they try to maintain the goal that in 2050 we would like to have a zero carbon emission, and with that, so we will be able to maintain the temperature rise within 1.5 degrees C. So this is a very important movement, and of course, with that movement is going to create some challenge and opportunity for the utility sectors. One of the important one, as the chairs mentioned, that the energy storage system, or more specifically, battery storage system, have been considered as a game changer with the number of the technologies that have great potential in meeting these challenges. And you have seen the most recent development on the hydrogen economy. Okay, well, this is not a new one. Actually, back in 1980s, the people are talking about the hydrogen economy. However, it's coming back, and this time is very strong. And then, in addition to that one, one of the most mature one is the battery storage system. And this is the subject that I would like to discuss with you. However, when you look at the stability of the storage technology, it's determined by the power and energy. Okay, we call it the power density or energy density, and the rate at which this can be stored and delivered, how fast they can change. So other characteristics considered are, okay, you consider the round trip efficiencies, okay, the cycle life, and the calendar life, or the safety, reliability, effect on the environment, and the run rate. So on this one here, when you look at this one here, you're looking for, okay, when you charge the basically store the energy, when you take it out, how many percent you can take it out. And for the power and energy density on the battery storage system, then we are looking at on this one here, you have a smaller one to the large one. And then you have from the time, okay, at the rate of charging, you can do it a second to the hours. So this part is on the energy density side. This part is on the power density side. And then, so you can see here, okay, yes, at the present time, that the two technology here is on the bulk power management, and the battery it's a scattered around into the different because of the different technologies. So you can see here that the NiCad battery, okay, or the metal hydride battery, or the recent one, the Lithiumion Battery, okay, or the traditional lead acid battery, and then or the sodium sulfur battery. So, and then some other flow batteries. So you talk about the different technologies over here. Then you can see on this one here, the deployment of the battery storage system in the US moved quite dramatically. Okay, so you look at it from the 2013, almost next to nothing until today. So, and then even, okay, the data I have is basically ended the second quarter of the 2019. However, you can look at the news. There are a lot more activity going, and then also you look at it even in California. In the CPUC require the utility company install 1.325 gigawatt of the battery storage system by 2020. So this is basically it's a fast-moving technology and deployment. So when you look at this one here, okay, this is how basically the trajectory and the accumulated energy storage system from the 2012 to 2024. And yes, at the beginning, the California basically moved very fast. If you look at the whole United States, then all others are catching up very also dramatically. And later I will discuss, okay, why California becomes so fast, and then that is the basically, okay, depends on their regulation and their operation protocol. So talking about, as I have mentioned, okay, for the battery storage system, we always have to look at it. What are their energy storage, the energy density and the power density. So you try to consider what is they have a different technologies, and then of course the lead acid battery is the most traditional one, and they can charge with the improvement, okay, from if you charge the cycling life, it's about 300 to 3,000, depends on the technologies, and of course we have seen a lot of improvement on the lead acid battery, and their efficiency, cycle efficiency, is about 70 to 90%. Okay, so their advantage is inexpensive. They are mature technology. However, their disadvantage is the limited cycling capacity for most standard type, and they have a relatively low energy density. And then because of the material, so they are environmental hazard. And well, the most popular one is the lithium-ion battery, and their cycling life is around 3,000, and then also the cycling efficiency is improving. So, and they also have a higher energy density, and they have a lower self-discharge rate. So when you put it up on the shelf and without using it, then the self-discharge rate is relatively small. And also, very important one is they don't have any memory effect. Okay, and of course, at the beginning of the development, this technology is relatively expensive. And however, with the development, with the improvement on the technology, we have seen the price drop dramatically. And also, they evolved the different lithium-ion related technologies for the battery storage system. And they are, because of their higher energy density, so the safety become a concern, and a lot of research has been put on the internal short circuit or the thermal runaway. Then the other one is the flow battery. The flow battery is basically, okay, well, on this one here, they has a long life. And however, if you look at efficiency, they are lower than the lithium-ion battery, and they are scalable, okay? And the lifespan is not depends on the depth of charge. If you look at lithium-ion battery or the lead acid battery, often we talk about the 20% or 80% depth of discharge, you have to leave some of the energy inside the battery. In other words, you cannot drain out everything. And but they require an electrolyte tank, and they have a relatively high maintenance. And because the flow battery, like a sodium sulfur battery, they are complex monitoring and control system. Besides, they are normally they operate at a higher temperature. It's because, for example, in the sodium sulfur battery, it's a molten salt, and they run at about 400 degrees C. The other one is the supercapacitor. Okay, so they have a high power density, but they have a low energy density. So on the supercapacitor, yeah, they can discharge very fast, and they have a longer lifetime, and also with the wide operating temperature. Okay, so that is basically, okay, well, there are a lot of the development recently, and yeah, if you look at some of the development from the support by Gates Foundation, and some of the operation, okay, from the Tesla, and then you can see there are a lot of development on the battery technologies, because when we talk to the automobile manufacturer, they say, okay, well, they are leading part. It's not the motor, it's not the controller, because everybody can design a controller. The key component the battery. They are leading, and then so yeah, that unfortunately with that situation, that a lot of time they are not they are not willing to release what the characteristic of the battery or the material that has been used inside the battery, and then it become a so-called proprietary information. They are commercial secret. However, from the power engineer point of view, we like to look at it is how to apply that battery storage system into the power system, and how can we utilize it in different level. On this one here, I'm talking about the transmission level, distribution level, transportation, and the consumer side. Okay, so let's talk about the transmission level. Then you can do the transmission upgrade deferral and the congestion relief. Okay, because if you look at the deregulation, a lot of time the price uneven in the power system because of the congestion. And with the battery storage system, we will be able to relieve some of the congestion situation and then try to reduce the possibility of price spike. Then if you have enough storage, you can do the energy arbitrage. Okay, so that you can basically get into the participate in the real-time marketing or an ancillary service. So you can do the load following. If the manufacturer on this one here, a lot of time they have a demand charge, so you can basically with the battery storage system, then you can do the peak shaving, and also you can, because of in the manufacturer, you are operating a large equipment, then that may create a voltage fluctuation in the system that affect the power qualities. So with the battery storage, then they can do the quick release and then improve the power qualities of the system. And of course, you can, with the battery storage system, especially if you can put into a microgrid, and then you can really improve the system reliability. Yeah, because one of the best example is the Hurricane Sandy in the northeast corner of the United States, and so some facility has a battery storage system, so they can avoid the power outage. And also some report talk about if we have a microgrid in that area, and then that will improve the resiliency of the power system. The other one is ancillary service. Okay, so this is on the power marketing side. You can do the regulation, okay, and basically you can do the rec up, rec down, or then basically get into the so-called fast response reserve. In the ERCOT market, in other markets, they have also a similar mechanism to involve the battery storage system. And then they also can help the frequency response, because the battery, they can do a very fast response, and with the current measurement, then you can do a faster response in the power system. Then also, if you look at some of the unit, we always have to prepare for the system blackout, and some of the generation unit will be tagged as a black start unit, and then with the battery storage system, then they can provide this kind of service. So I have seen some of the power plant, because they try to do the black start, then they have to either install the diesel generator inside the plant or put the battery storage inside the plant. On this one, and at that time, I have seen all the battery storage is basically sit on the shelf waiting for the outage. So with the current setup, the battery storage can be installed outside of the plant, and then they perform their duty daily, and then also serve the purpose for the black start. They also can do the reactive power support. So yes, that I believe some of you have seen the story, and of course recently, we have seen a lot more news. And the first one is a Tesla. If they put in the 100 megawatt, 129 megawatt-hour battery in Australia, in the South Australia, and then they have seen some big improvement on the system reliability in the region. Okay, so the other one is okay. When try to look at it, okay, from the renewable energy point of view, and this is part of my research. It's a long time ago, and at that time, when we look at it, because when you try to look at the renewable energy, and they are intermittent in nature, so we always have a dream or have wish that one day renewable energy can become dispatchable. Okay. However, from the intermittence to the dispatchable, there are several stage that we can explore, and this is we consider the second stage, make the renewable become a dependable source. Okay, so if you look at it from the power system operation point of view, the power system operation that for the system operator, they are going to operate the system, or we call it a dispatch cycle. And because of the renewable energy, most of the power system operator move their deployment cycle from 15 minutes down to about 5 minutes. And with that, so if the renewable energy can consider, say, okay, for this one here, this study here, say, okay, we can put in a small amount of battery storage and then try to basically smooth out the renewable energy and then give the prediction. You can tell the operator for the next 15 minutes or next 20 minutes. This is the amount of the energy or amount of power I can give you. How many megawatt fixed for the next 15 minutes. And this will become very helpful for the system operator when they perform the economic dispatch, because this one become a dependable source, and then so they don't have to worry about the intermittence of the system. And of course, a lot of time people talk about the renewable energy, talk about battery storage. They will always tell you, yes, ideally you can store the surplus at the nighttime and compensate it or use it in the daytime. But with that technology, yes, that if the battery is cheap enough, then that is the feasible one. However, at the present time, that is a huge amount of energy storage requirement. So what we try to look at it is how can we break into the different step and then start it from the intermittence in nature to the dependable source. And this is basically on that I have mentioned on the break start service. So that is basically, if you look at the procedure over there, then during the blackout, you energize the transmission line and then probably pick up some of the load, because a lot of time if you just energize the transmission line, then you may end up with over voltage issue because of the line charging. So you can basically along the way plan ahead and then pick up some of the critical load and then maintain the system voltage. Then with that, you can provide the energy for the generator to start up, and then you can ramp down the energy storage when they accomplish the goal of starting the first generation unit. So this can be served as a break start service. Then the other one is people also talk about with the renewable energy, because the renewable energy has a smaller inertia. And then you can see, once they increase the penetration level of the renewable energy, the system inertia reduced. So in other words, for the same amount of fluctuation, the frequency fluctuation will be bigger. So there are some utility, or some company that requires some inertial requirement on the basically, this is the data in the 2011, so it's a long time ago, and then now that's basically with the moving technology, this one, the requirement is getting stricter and stricter, and then basically, that battery storage the role of the battery storage become more important. And the idea for the improved inertia is that because if the system inertia is reduced, then for the same amounts of the disturbance, the frequency drop will be much higher than with it's a good inertia of the system. So they are looking for the possibility using the battery storage to create a so-called virtual inertia through the control of the power electronics. All right, so you have to basically, you have seen a lot talk about the droop control or the frequency control, look at the frequency or look at the DFDT. And the other one is, okay, they are not unrelated. Some people also use the battery storage in the DFIG in the middle part. If you look at the grid side converter and the source side converter in the middle, they require a DC part, and some technology use that part, install the battery storage at that part, and to improve the system inertia to provide the inertia of the wind generation. Okay, so we try to look at it, and of course the control, it's basically you try to do the more like a steady state control, you try to do the more dynamic control. Okay, so people look at the droop, and you can look at the voltage droop and the frequency droop, and also you can look at the frequency or the DF, the frequency deviation or the frequency change rate. Then depends on the requirement, and then you can design your power electronics controller to respond to the system situation. Then the other one is, okay, I'm using ERCOT as an example, and then they started from the 2017, so they implement. If you look at it on the ancillary service or the frequency service part, we look at the regulation service, the reg up, reg down, okay, regulation up, regulation down, and then also the historical, we call it the spinning reserve, and because at that time the reserve come from the generator, spinning generator. In other words, generator cannot generate the full power. They have to reserve something to face the emergency of the system. And later, because of the development on the smart grid, low participation will become possible. So we changed the name from the spinning reserve to the response reserve, because like in the ERCOT system, about 50% of the reserve, this response reserve, come from load. So they are no longer spin. That's the reason why we changed the name from spinning reserve to response reserve. And in order to have the participation of the battery, and also, of course, some other load, because when you define the regulation service, you cannot target a certain technology. You basically, it's a performance based. And in the ERCOT system, we call it a faster responding reserve. Okay, so they have and the battery storage system become one of the most favorable candidate for this type of the reserve. And for the batteries, as I have mentioned, okay, in California, we have seen a lot of development in the battery storage system. And in the Texas, they are relatively slow, okay? And this is because of the operation protocol of the power system. And if you look at the operation protocol of the power system here in California, they install the battery storage in the grid, okay? So they consider that one is for grid improvement. And however, in Texas, we consider battery storage is a generation facility when they are discharging, and they are controllable load when they are charging. Okay, so they use the two model to describe on this one here, and also they create a so-called fast responding regulation service for the battery storage system and others. Okay, so this is some record from 2017 to 2018, and then the capacity is going up, And in 2020, the situation is moving along. I look at the 2020 record, it's moving along very well so far. And of course, in the ERCOT system, they try to look at and say, okay, well, instead of putting the two hat on a battery storage system, consider it's a generation facility when they are charging, when they are discharging, and then consider they are controllable load resource when they are charging. Right now they try to develop a single model for the battery storage system, and schedule to deployment is 2025. In the distribution system, that on the right hand side, this is the very famous so-called duck curve. And so with the installation of the renewable energy, especially in the rooftop, the solar, and this is happening in California. And so during the daytime, people go to work, and then so actually the power consumption, the net load is reduced. It's unlike the traditional power system, we always see the peak in the summer day in the afternoon, and on this one here, the peak happened at the sunset. Okay, so it looked like a duck, and then you can see on the right hand side, the RAM need is about 13 gigawatt in 3 hours, and I always wonder, okay, is that the reason why that they put in the 10%? It's 1.325 gigawatt, okay, on the battery storage. So yeah, that is basically that battery will be able to help this situation. And then they also can do the voltage excursion support. They can do the grid support because and the end of the feeder, then that can create, they can do the voltage regulation and then try to maintain the feeder voltage. Okay, and the other one is, okay, well, that some company put out put the battery storage under the pad mount transformer. So when they serve the community, because some of the community residents, they require more reliable power because of medical reason, and then they're looking for the community UPS instead of individual house UPS. They put in the community UPS, and with this one, they will be able to improve the power quality. So we look at the distribution level. We like to improve the reliability, okay, reduce the steady safety of the distribution system, and then this is one of the possible approach. Try to secure reliable power for the customer who are needed. So from the residential side, and you can see, okay, Tesla has some they provided some power, the power bank, and then so on that one it's about 13.5 kilowatt hours, and then so they have a good round trip efficiency. And of course the other companies, okay, I have seen some development from Panasonic, from LG, and the Samsung. They have a similar technologies, so you can see a lot of other development over there. And for the transportation side, you can see, okay, from the EPA, that from the greenhouse emission point of view, the transportation electrification is one of the most active move in the recent industry, and we try to convert the gas power transportation vehicle into electrical. So the transportation electrification is in the move. And from the EPA, this is a 2019 result from industry or from the transportation. From the transportation, it accounts for 29% of the greenhouse gas emission. And with the COP26, we'd like to reach the net zero carbon emission, okay, by 2050. So this one, the transportation electrification become a very important part. So you can see, and then also, well, even we use the electric vehicle. the electric vehicle is as clean as the source. So if you use the coal-fired power plant to generate the electricity, then you basically just transfer the pollution to the different location. So we like to look at the idea or look at the possibility that how can we utilize the renewable energy. And this is also one of the research that I'm doing. Then we look at the so-called source variability, and especially on the renewable energy side. And you have a variable generation, you have a system load from the customer side. So basically in the power system, you are going to see a lot of source of variability. And then how can we identify the source of flexibility that can cope with the variation of the power system? So one of the idea we have come up is, okay, well, I have this one here. I have a charging station, okay? And the charging station also a distributed energy storage system. So they will be able to look at this one here, and then we call this one here, this is the source of variability that you have a wind generation, you have a photovoltaic. But the source of the flexibility is your charging. You can have a flexible charging. So flexible charging, as long as you know how much the variation in the power system, and then for the charging side, you can provide a counter. And so we talk about the idea, say, okay, well, is there a possibility that instead of purchasing, when you purchase in the power, you purchase in how much? For example, we call that one is a virtual wind farm. Okay, I have a wind farm, it's far away, and I'm here. So I can talk to him, sign a contract, bilateral contract, say, okay, I'm going to purchase 10%, whatever you generated. And then I will distribute it along my battery storage infrastructure here. So on this way here, if they generate 100 megawatt, I will take 10 megawatt. And of course, I can do, based on the SOC, I can take this 10 megawatt and repackage it and sell it back to the power system if it is a variable. Okay, so on this way here, if the owner of the wind generation can take up that, basically, okay, find a customer that they can take up 100% of what they generated. So on that way, basically their variation will be offset by the flexibility part, and then that will minimize the impact of the power system. Okay, so this is the battery storage system. The other one is the battery swapping system, and this is the picture, the photo I took it in China, one of the station, demonstration station, and then they basically use the robot to basically replace the battery on this way here, because we always complain it takes a long time for the battery charging, and with the swapping, that I count the time of this video is about 2 minutes 40 seconds. So you will be able to swap the battery out and then replace the fresh battery for the car, and they are ready to go. So they are almost compatible with the current gas station on the time consuming side. Okay, and then the other one is for different application. Okay, on this one here, because when you look at it, okay, well, some of you may have a USB power bank, and that is good enough. The battery storage system is good enough for your cell phone, or good enough for your basically watch. So the different application require different capacity, and also depends on how much time they need it. Okay, how long they need it. For example, if you try to use it to improve the power quality, and then if you try to avoid the voltage sag or power disruption for home or commercial or industrial, then that is basically you're talking about 10 seconds or 10 to hundreds of kilowatt, and the duration can be a second or fraction of the second to the minute. And then for the distribution energy storage system, then you're talking about, okay, about the 10 to 100 kilowatt, and then it's the requirement is become hours. For the T&D, then that size is increased, and you are looking for the system support, then it's basically it's hours. If you just for the renewable integration, then that can be on the minutes to hours. And then for the wholesale service, then if you do the frequency response, then it's on the minutes. If you try to do the energy arbitrage, then it's hours. So depends on application, that require the size requirement and the duration is different. Then the other one is, okay, well, we always tell people it's difficult to build up the reputation and easy to destroy it when you introduce a new technologies. Okay, so that's the reason why we always emphasize that you have to basically have a very good recommended standards, regulation, or government policies to deploy the battery storage system. And we have seen a lot of accidents happen, and that basically, okay, ruined the reputation of the battery storage system, and then that created some impede or some difficult resistance for the deployment. So you try to look at it from the system component point of view, like, okay, UL 1642 talk about the lithium battery, 7041 talk about inverter, converter, and control. Okay, so this is on the system component and the type. Okay, so like a NitroBoy 1547, the interconnection requirement, it's not the focus on just the battery storage by itself. They focus on the distributed energy resources. And then also the storage architecture. So how they come out the standard, the type, and the storage installation, because the safety is a main concern. Operation, yes, of course, you like to have it operate as intended. However, the safety of the operation is very important. And then once the installation, just like a generator, new generator, you need how are you going to do the commissioning? Okay, what is the procedure to do the commissioning? And then the operation and maintenance, and then if something happened, so how to respond? Because this is a new technology, and I read a report recently that there's a car accident happened in California highway, and they talk about how they removed. It was an electric vehicle. It was involved in an electric vehicle, so they say, okay, in normal case, it takes 1.5 hours for the rescue group or the firefighter to clean up the highway and then reopen it. For that incident, it took them 6 hours, and they have to call the engineer from Tesla to basically remove the battery, because during the cleanup, they heard the pop inside the battery. So they feel that basically the safety is their concern, and so that is the basically, okay, we have to write up the SOP on the instant preparedness. And then the other one is, okay, well, for the storage system, electrochemical energy storage and the safety, you try to look at the reliability and the aging, and also the scalability, and also the risk associated with internal fault. Because we have seen a lot of study talk about internal fault of the battery, some run away, but we also have to look at the external fault, the arcing current, and how are we going to calculate the arcing current, the instant energy, and the protection boundary for the DC arcing fault. Okay, and also of course the protection of the battery of the system, it's quite different. Okay, so if you look at the battery system here, they can have an AC fault, they can have a DC fault. So depends on where is your fault location. Okay, and the AC fault and the DC fault are different. Okay, this is one of the tests I have performed in the lab, and try to look at the AC arcing fault. And this is the slow motion video. You can see for the AC fault, you have a zero crossing. However, for the DC fault, then you don't. Okay, so for this one here, the DC fault doesn't have a zero crossing. So in other words, if you try to cut out, especially with a large current, if you try to cut out current, then that requires some treatment. Okay, then yeah, when we talk about the safety, and as the chair mentioned, I was the project manager for the IEEE NFPA arc flash phenomena, perverted arc flash phenomena research project, and I have done that research for since 2008. Okay, so the AC site, the three-phase AC site, has been published in the 2018, the IEEE 1584. And now I'm working on the single phase and the DC side. So then when you try to look at this one here, what is the factor that affect the incident energy is the voltage, current, configuration, gap, arc duration, and the working distance. So you can see here, on this one here, this is a horizontal. And we consider this is the person standard here. You can see when an arc happen, then the plasma basically flow toward to the person. For this one, it's a vertical configuration. It's going down, so the person standing here, and then probably the low part of the body will get hurt, but not the upper part. And for this one here, it's a smaller current, so that arc is confined inside the enclosure. So you try to look at the different situation, and then you try to provide a proper protection. And then, of course, before you can provide a proper protection, you have to find a way to estimate the level of the damage or the level of the severity. And so this is the basically, that is the my consideration is, okay, well, how are we going to, because we see a lot of development in the DC side, in the battery storage side. Then in the US, okay, we see two standard. One is IEEE 1584, or they are related guide, and the other one is NFPA 70E. Okay, and the NFPA 70E, that basically even they give some table, okay, on the DC side. However, that it's not a very rigid issue, and then we think, okay, well, it is time that the IEEE should develop a very similar standard on the DC side, DC arc flash side. And also, the other one is, okay, it's a big move, is how to do the safety by design, and how can you design the arc, because on this one here, it's difficult to show, because we initiate arc at this point, and then we create a weak point somewhere else. So when the arc happens, it will transfer. Okay, so it will move away from the arcing point, the arc energy away from the person. So that created some safety. So this is the basically how you design the system, and we call it the system by design, safety by design. And then this is also when we try to develop the battery storage system in the power system. This is also a very important criteria that you try to design this one. And yeah, with that, I'll conclude my presentation. And then if there's any question that, yeah, I'll be more than happy to discuss with you.
Thank you very much, Professor Lee. I don't know if you can see the chat. There is a question from Ariel Santos.
Okay, let me turn it off. And yes, now I can see that. Okay, it's in the weak power system, the frequency regulation problem. Okay, so it's basically, okay, the difference between the maximum minimum demand and so from the, if you look at the the weak power system. Weak power system, then they have several different problems. All right. So I have seen some weak power system. The first one, that their short circuit current is relatively small. Okay, so that battery storage system may not be able to provide, because from the fault protection point of view, the battery storage system may not do much because the power electronics, the constraint on the power electronics. So I have seen in ERCOT, when they try to develop on the fault detection side and try to apply a traditional fault protection, they use a synchronous condenser. This is the one thing. And if you try to do the voltage regulation, yes, then it really depends on the size of the capacity of the battery and then the response time. So you basically try to use, a lot of time, I always tell people that we should use a hybrid system. Okay, so you try to use the high power density unit as a beginning to provide the initial response, and then also provide the higher energy density part to basically make it last longer. And so with that coordinated response, and if you even look at it in the Tesla 100 megawatt, 129 megawatt hour battery, they also separate into two groups. One group has a higher response, the faster response, and the other group has a slower response. So, and you have to basically, okay, the maximum and the minimum load. Yes, you do have to consider that one, because when the load change, and then that basically the impact, the variation, the same amount of impact variation will have a different impact. Okay, and then increase the renewable energy. That also, because when you increase the renewable energy, you reduce the inertia of the power system. So you do have to study that part, and then either use the virtual inertia, or you try to basically use a generator, the traditional generator, to cover that part, or use a battery storage. And the battery storage basically provide the virtual inertia. And what aspect of use should be focused on the storage energy system, on regulation, load following. Okay, so this one here, it's basically, it's a multifaceted issue, because for the first one, the regulation has to be clear. Okay, as I have given an example, in California, they consider battery storage system is for system reliability improvement. And if it is a system reliability improvement, the transmission company, when they install the battery storage system, they do the cost recovery through the rate. So general public, it's basically write the cost into the rate base. So they recover it's a guaranteed return. But in Texas, since the battery storage system is considered a generation facility, the line company or the transmission company, they cannot own a generation facility. So that also, actually, it's created a lot of debate in Texas. And but currently the situation hasn't changed yet. So the batteries, since the battery storage system is from the regulation point of view, is considered as a generation, and also the controllable load. So they belong to IPP. Okay, it's a generation facility. There's no guarantee of return, and that also impact the development of the battery storage system, unless we create a favorable market for the battery storage system. And or the price of the battery storage system becomes small. And then the other one is, okay, well, it really depends on the policy of the country. You try to solve the problem locally, individually, or you try to solve the problem integratedly. For example, for the renewable energy, and the renewable energy by itself, that each wind generator or each wind farm can have a storage system to smooth out variation of the output. So in some of the regulation, they do require the variation of the output have to limit it in certain percentage within certain time frame. And then that battery storage will be able to do it, or you can have a centralized integrated system. So, and then depends on the size, depends on the response time. So it's basically also depends on application. Just like in my presentation, a different application require different size of the battery, different response of the different response. Okay, different size of the energy and this different response time, the response speed. That is basically related to the power density. Okay, and then the other one is okay for the. Well, you have to translate it for me because it's in probably.
No, it's okay, Professor Lee. The other question is for other aspects of the organization of the event. No technical questions.
Okay.
So no problem. Thank you very, very much for your very interesting presentation. I would like to ask you only one more question because we are 4 minutes to be at the end of the session. From your point of view, in future, what would be the predominant technology that you think would be used for in power systems in terms of energy storage? Do you think will be driven by the transportation business? I mean, lithium batteries, or could be other type of batteries as you presented, like flow batteries or whatever. What is your opinion on that?
Well, this is the basically okay. Well, I would say all of above, because it really depends on the application, and then depends on the density. Like just like in the U.S., they have installed a flow battery in, I believe, in Virginia site, and then that is for the community. They have a single serve, and they use a flow battery to provide the community in case there's outage. And also the flow battery, the response time also improving. And as you say, the flow battery can last longer and they don't have to worry about the depth of discharge. And the lithium-ion battery, yes, the lithium battery, that is the basically, okay, well, they progress it very well. And then you have seen a lot of other related battery technology show up. So in general, battery storage system will be there. And then of course, a lot of technology are driven by the transportation electrification, because for the transportation, we would like to have it, you can have a one charge, you can drive a long distance. So that come in with the energy density. And you try to drive your car from 0 to 60 miles in 4 seconds. Okay, that is your power density. So that is basically it's driven by that part of the technology. And the other part of the new kids on the block is the hydrogen. Okay, so yes, as I have mentioned earlier, that is also a different type of energy storage system. But you can see that this development moved up quite fast in recent years. And yeah, we are talking about the so-called green energy, green hydrogen. Okay, the hydrogen produced by the renewable energy, or a blue hydrogen, or even a gray hydrogen or black hydrogen from the coal-fired unit. And yes, so that part of the energy storage is also, it basically has a great potential in the power system.
Thank you very much, Professor Lee, for your presentation and for the responses to our questions. And well, hope you have a nice day, a nice Congress, and hope to see you soon in other sessions. Thank you very much.
Yeah, thank you very much, and thank you for your attention. And if you have any question, that you can send me an email. And so yeah, I'm with the University of Texas at Arlington, and my email is almost like a public domain information, so you can find it relatively easy.
Thanks a lot. Many thanks.
You're welcome.
Okay, so we are on time, and we then close this session. Thank you all for being here, for all the participants. We have been around 40 in this session, so thank you very much for attending, and we'll see in the rest sessions of the Congress. Bye-bye. Have a nice time today.
Okay, have a nice time, and whoever in the U.S., happy Thanksgiving.
Happy Thanksgiving. Bye-bye.
Okay, bye-bye.
Bye-bye. Bye-bye.
Bye-bye.